in this lecture, what we'll be seeing how operating systems are structured, or what are the different ways in which we can design and implement an operating system. Okay, how to design, or what are the ways in which you can make an operating system exist in your computers. How you design a operating system. Okay, so when I say structures, it means that we have a pattern or a system, right? So we'll see what are the patterns or the systems that exist in an operating system. So whenever we try to design an operating system, we have to have 3 points in mind in the point of view of a user. A user who is going to use an operating system, he should have these 3 points in his mind, so that these 3 points are being satisfied. Okay, first thing is that multiplexing of resources. Multiplexing of resources means we have a limited resource. Say we have only one printer, we have to use this printer for so many users, right? Multiplexing of resources. You have a resource, you have some memory space, you have some input output device, or you have any kind of resource. Multiplexing of resource means one resource being used by more than one number of users or processes. Okay, so multiplexing means several processes can run and use resources concurrently. Hence, time sharing between them. Okay, you are sharing the time and utilizing the available resources in the most effective manner. Second point is isolation of resources and processes. Each person should have his own method and his usage of these particular resources. It should be multiplexed as well as it should be isolated, right? Isolation of resources and processes. Contention for the resources to be fairly arbitrated, and a process should not interfere into the address space of another process. We have multiple processes that is happening within the system. Okay, each process should have its own independent space so that another process does not interfere with this particular process. This is called as isolation. Multiplexing means we have two different processes, both the processes should be done, addressed, that's it. Interaction among processes. Multiple processes you have to have an interaction between one process and the other. For imagine that you are giving one process to a particular point and the other one to another point, and you need this communication to happen. When one process is idle, you can utilize that process for the another purpose. So these are the point of views that a user should have while designing an operating system. Is that clear? It's the user's point of view. Next thing what we'll study is we'll study the designer's point of view. As a designer or as an engineer who is going to design an operating system, what are the things that we have to have in mind is the next point that we are going to study. Is that so? As we were discussing the previous slide, we have discussed the user's point of view. Now we'll be discussing designer's point of view. So in the designer's point of view, we should have two important points, that is portability and extensibility. What is meant by portability? Portability means the capacity of the operating system to be used anywhere. The capacity of the system to be used in different conditions, in different hardware architectures. So when you are designing an operating system, you have to keep in mind that you have to, your operating system should be capable of working in different kinds of hardware architectures. Is that okay? Extensibility. So that extensibility means Every day things are getting advanced, right? Previously we did not have touchscreen phones. Now touchscreen is very common, right? So when things are changing, we should be able to adapt to these changes. This adapting capacity of an operating system is called as extensibility. And whenever you design an operating system, you have to keep in mind that your operating system should have these two very important features. The first feature is portability. Portability means that it can adapt to any new hardware situations, hardware components or equipments. Extensibility means development of new features. Instead of hardware, it is features. So now we'll see a very important definition which you need to understand. What is a kernel in an operating system? What do you understand by the term kernel? Okay, I'll better use a highlighter so that what do you understand by the term kernel in an operating system? It is a very important definition, or it is an important term that we'll be using throughout in this course. So if you have not understood what is a kernel right now, it might be very difficult for you to understand the topics that is coming in future. Is that clear? So kernel means the central core component of the operating system where all the process, all the things are happening. The kernel is a place where all the important events or important process or every important things are happening. This is a central part of your operating system. Okay, the kernel is the core component of an operating system that manages system resources and enables communication between the hardware and the software. So whenever I say or use the term kernel, you should not say that I did not understand what is kernel. This is a very important and fundamental concept that you should keep in mind. So it operates at the lowest level of the operating system and ensures efficient execution of processes, memory management, and device control. So kernel is the central part. All major operations in the operating system takes part in kernel. So you will be using this term very often. If there is any problem of understanding what is its definition, you can get it clarified right now from me. Okay. So like kernel, we have another important concept called as bootstrapping or booting. Whenever I switch on my system, what I am doing is that I am booting this operating system. I am giving power to my processor. This process is called as booting or bootstrapping. Okay. Bootstrapping or booting is the process of starting up a computer by loading its operating system. When you switch on, what happens is that it searches for the kernel where there is the operating system loads. This process, the starting up of process, when you see that Windows or Linux coming up, this process is called as booting. Booting means loading the appropriate operating system softwares so that your computer gets started or switched on properly. This is called as bootstrapping. Now I'll dictate these things. Bootstrapping is the process of starting up a computer by loading its operating system into memory from a powered state of. It is initiated when a computer is turned off or restarted. Restarting in other words can be called as rebooting also. Understand? Rebooting means you are loading the necessary operating system softwares once again into the system. Okay? So what happens when you switch on? The kernel takes control of the computer after bootstrapping and provides the services. We have already discussed some services, right? Services to the system and its users. Some services are provided by other system modules of the operating system. What are modules? What is a modular approach? All these things we'll be studying in detail in the coming lessons. Okay. So one example I've given you, system D. Okay. Shall we proceed with? I hope you have understood what this is, right? Next is where we are going to start this topic, which is called as monolithic kernel. What is meant by monolithic kernel? There are different types. First one is monolithic kernel. Second thing what we'll be studying is about micro kernels, microlithic kernels. In monolithic kernel, the entire kernel is stored as a single one software. Okay. Kernel, I told you, is the core of the operating system. The entire program or the entire system is stored as a single program. And from one particular program, everything is being accessed. This is called as monolithic kernel. Next, we'll be studying what is microlithic. We have different other types also, one by one we'll be studying. Okay. So, in monolithic kernel, the entire operating system runs on a single program. And all those services that this particular operating system is going to offer to the users will be taken up from this one particular program. In monolithic kernel, only one program is there at the core of your operating system. This kernel provides file system, CPU scheduling, and these are the general services that these will provide. Say CPU scheduling, memory management, and other operating system functions through system calls. We have a separate topic called as what a system call is. I will teach you what a system call is in detail. Don't worry about that. Okay. So in monolithic kernel, there is one program that is being used by the operating system to serve its users. Clear? So next is a very theoretical question that often comes in your exams. What are the advantages and disadvantages of monolithic kernel structure? Okay. Monolithic kernel, you have a single program in the kernel and the single program executes all the operating system services. Okay. So the advantages, what are the advantages and what are the disadvantages? A very common question, theoretical question, and it's given a very simple self-explanatory answer. That first point is that it is very simple because you have only one structure, centralized, so that everything you need to approach only to this one particular program. So it takes lesser time also. Close coupling and performance is better. I told you, when there is only one program, when there is only one person to approach, things are much more easier, right? The same way, when there is only one program, things are much more easier. We have so many advantages, but disadvantages overcome the advantages. That's why we opt for microlithic structures. Very good. Mani nache. So having seen the advantages, now we'll see into what are the disadvantages of using a monolithic kernel. So disadvantages in points, we have only one program, so naturally the size of the program is big. Adding new functionality means you have only single one. If you wanted to add something new, it might be a big problem. Okay. And if there is an error or a bug in one particular part of the program, it might affect the entire program. Okay, that's the biggest problem with monolithic kernels. So this is a simple diagrammatic representation of a monolithic kernel. We have these controllers, we have a kernel interface hardware, we have signals. All these things are controlled by a single system called interface. Okay, we have a kernel interface to the hardware. See, kernel, I told you, is the central part of your operating system. It connects the hardware and the operating system, right? All the contacts that is going to happen with the hardware is done through the kernel. Okay, so here in the topmost layer you have the users, and in the bottommost layer you have the hardware components. You have commands, compilers, interpreters, and programs, internal programs, and so on. And then this gets connected to the system terminals. Okay, having seen the monolithic means single, microlithic means you'll be having multiple small programs. Very easy to understand. So we'll see what a microkernel approach in building an operating system means. Okay. So in microkernel, it means that the entire program is divided into micro modules. So you have this modularization. Modularization means you are dividing it into different kinds of modules. This is called as modularization. Okay, you are dividing, instead of having a single big program, you are dividing it into different modules, and this structures the operating, and this creates a structure, right? By removing all non-essential components from the kernel. Whichever things that are not important are removed from the kernel. Okay, and implementing them as a system and user level programs. OS kernels provide minimal process and memory management with inter-process communication facilities. You have two process, so you have inter-process communication facilities when it is divided into multiple programs, right? But if you have a single program, you don't have that facility, right? Are you able to understand? The bulk of operating system services include device drivers, file system, system call handling, and are run as a processes. And these are called as servers. So what is a server? So these things are called as servers. Servers means something that is going to give you something. Okay. It could be memory, it could be time, it could be process or anything. So here what we are doing is that we saw this OS kernel provides minimal, so we are separating from the kernel. Kernel will contain certain programs. Outside the kernel also you will be having certain programs, so that it is very easily accessible and can have multiple processes working at the same time. Okay. What are processes we'll be studying in the second unit in detail. Processes both user and system levels are alike and interact with the operating system servers using messages passing via OS kernels. So through the kernels we have a link towards multiple processes. So this is the architecture of a microkernel. You have the hardware here. You have one module exclusively for inter-process communication, memory management, CPU scheduling. You have user modes. So you have this kernel divided into micro kernels, sub modules. You have the multiple modules, and each module has an access to its own system. So next, as we have seen, we'll see the advantages and disadvantages of using microkernel. Okay, microkernel advantage. First advantage is high portability because you can have it in modules, right? It is highly flexible. Is that okay? It is highly flexible because it has good portability. Second one, highly reliable. You can believe if one module fails, the other one will take it up. Okay, easily extensible. These were the factors we have discussed while in the initial stage, first pages. We have discussed, you remember that portability, extensibility, all these things should be there when you design a good operating system. So, micro kernel provides all these advantages like good portability, reliability, easy extensibility, and so on. So, what are the disadvantages of using a microkernel? Increased communication means you have more energy, you need more power, right? When you have it in difficult modules, you have different kinds of modules. You need to communicate within these modules. So what are the difficulties? You can use your common sense and find out certain kinds of things that is being specified here. Okay. So when you have this, you need to divide it. And so when you divide it, you need somebody to control it, right? Yes or no? That is one disadvantage that we have with respect to one disadvantage that we have with respect to microkernel, increased use of space. When you have more communication, you need to have more spaces. When you have multiple modules, you need to have more space. Okay. And when you compare the performance, monolithic is better. The performance is not as good as the monolithic. But still we have more advantages. That's why we have these microkernels also. Okay. The overall workload of the kernel, the entire system will have more work. So naturally it will take more time. Naturally what happens is that you have communication. So you have possibilities of errors. Whenever you have multiple modules, you have possibilities of errors, right? So these are the major disadvantages. These are the points that might fetch you full marks in your exams. So ensure that you have noted down this. And so the diagrammatic representation of a monolithic kernel and a micro kernel. You can see that there is more inter-process communication that is happening between these kernels. So these are monolithic kernels. You have the hardware here. You have applications on the topmost layer, and it is getting connected to a single one set of programs. Microkernels, you'll have multiple programs. So when you draw these diagrams in your exams, it makes the examiner understand that you have conceptually understood these topics, so that they don't need to read your entire answers to give you marks. Another one approach other than this monolithic and microlithic is called as a layered approach. So the entire operating system functionalities are divided into multiple layers, and each layer has its own particular set of functions to be performed. You know that operating system is a very complex program, right? It's a very complex software. It has So many things to do. So what we do is that in the first case, we took the entire system to be one program. The next case, what we are doing, see, I'll show you examples also. We don't know whether you have used it or not, but I'll show you examples on how these operating systems are really working with. So in this approach, we have the first layer to be the hardware layer, second layer, third layer, fourth layer, and so on. And each layer is performing one set of functionalities. That is called as a layered approach. So the entire functionalities of operating system are divided into well-defined layers, where the innermost layer deals with the bare-bone hardware, that is the hardware. Uppermost layer is the service layer, where the users are accessing. Okay. In between, each layer interacts exactly with an upper and a lower layer and facilitates communication across the layers. Different layers are there. Each layer you need to have a communication. So layered approach is different from microkernels. Okay. In microkernels you have different modules. In layered approach you have different layers. So there is one layer, above that there is another one layer, and there is a layer, interlayer communication. And each layer has specific and limited functionalities and can directly use services only of immediate lower layer. Similarly, can directly serve one immediate upper layer. So this is the diagrammatic approach of a layered approach. This is how the diagram looks like. You have different layers, layer 1, layer 2, layer 3, layer 4. You have multiple layers here. You can assume this to have you can assume this to have so many layers here, and you have communication between layer 1 and layer 2, layer n and layer n minus 1. Okay, the communication happens between layers. This is a layered approach towards operating system. So we'll see the advantages and disadvantages of layered approach. Advantages: portability. You know that you have multiple layers, so it can be easily ported. Isolation is still available because you have things in different layers, right? Transparency. The third point is transparency. Upper layers need not know the details of the lower layers. This also offers simplicity. So operating advantages of layered approach. Advantages: number 1, portability. Each layer can independently each layer can be independently designed, maintained when the layers are well defined. Okay. Isolation. The layers can interact only through a predefined set of interfaces and cannot interfere with each other's address space. Portability is the first, second one is isolation, and third one is transparency. So the next point is about the disadvantages of layered approach. Lack of consensus. There is no consensus among the layers. So when you have layers, you have difficulty in accessing through the layers because you can access only one layer which is above the previous layer. Okay, layer, and you can access above that. So you have no consensus. Stratification is difficult. The layers are easy to work with if already well designed. So it takes a lot of energy and pressure to well define a layered approach. And creating these layers seem to be very, very, very difficult. The next point is about increased communication. As usual, you know that there will be more communication. Yes, because you have multiple layers, you have more communication. The next approach towards creating an operating system structure is called as modular approach, where we have loaded kernel modules. Okay, these things are different from microkernels because you have modules, but each module is differently loaded in the kernel. Understand? This approach is called as modular approach, where you have loadable kernel modules. So example for a modular approach, we have Sun Solaris operating system, where we have different modules. An example for a modular approach, Solaris operating system, where you have multiple modules, devices, bus drivers, and so on for individual modules. We'll complete it. Another one approach is called as hybrid approach. Hybrid means you have all these things included. It could be a modular approach and all these things. So examples of this hybrid approach, you have Mac OS, iOS, Android. We have a hybrid approach, and we have in practice what we do is that most of the operating system use different features. One may be layered, some part may be microkernel, some you have the entire things to be done in one particular phase, and so on. So in hybrid approach is the thing that most of the operating systems are working on. So far, this is a final slide where I'm going to give you summary of what we have done so far. We have studied the different structures of operating system, beginning from a monolithic structure, microlithic kernel. Microkernels means you have multiple things. You have layered approach, you have modular and hybrid approach. So thank you all. Thank you very much for listening to me. Thank you for your patience.